Okay, so thank you everyone. Someone told me that if the room's talking, then you should say something very quietly. All right, thank you everyone for showing up for this wonderful colloquium given by Joe Redmon, who comes to us from the University of Washington. As you can see, it promises to be a pretty fun colloquium. We don't have a trailer for this, but everything seems good. So Joe comes to us from University of Washington, where he works with Ali Farhadi. He's well known for YOLO, which is an object detector. Many people use it, darknet, and many other things having to do with computer vision, neural network. He won the best paper honorable mention in CVPR, which is a huge, prestigious conference in computer vision. So let's welcome Joe and look forward to his talk.
Thank you. Oh, okay, I gotta keep my voice down a little bit with this microphone. So I work on a problem called object detection, which is one of the core problems in computer vision. And the basic idea is just, you have an image, you want to figure out what all of the objects are in an image and where they are. And so obviously in this image we have a dog and a bicycle and a truck. It seems, like a fairly simple problem, right? Detection is super important just because going forward, it seems like increasingly it will play a role in just kind of everyday life, right? Self-driving vehicles rely on object detection to find obstacles and avoid other cars. I think there's a huge space for assistive technologies to help people who have visual impairments or people with other needs to use, say just like your cell phone to explore the world around you to understand what's going on. Robotics also heavily relies on computer vision systems, detection in particular, to make models of the environment that they're in to understand what's going on. So detection is sort of this really key component in a lot of computer systems that will sort of be that already exist or will be very soon in our future. So one question we might ask is, we want to do good research. What makes a good object detector? And the first thing that kind of makes a lot of sense is, well, we want our detector to be accurate, right? Systems are using this to model their environment. If our detector isn't very accurate, then we start running into problems very quickly. Our systems start breaking down. So accuracy obviously is a key component. Another thing that we want is speed, right? We're using these vision systems in real-time applications, and we want our systems to be able to make decisions very quickly about the environment. The environment is always changing in the real world, and obviously if you don't have a system that can recognize obstacles in time, you start running into some problems very quickly. And the last thing that you might want in a detector is some notion of scalability. So the visual world is very rich, it's very complex. There's lots of different objects out there. We don't want to shoehorn a lot of things into sort of similar categories. So, we want to, for instance, recognize the difference between, say, a cat and a cat. So some notion of scaling up to more classes to be able to capture this rich data that we have and be able to model effectively is definitely really important for a problem like object detection. So we have these three components of things that make a good object detector: accuracy, speed, and scalability. And a lot of prior work has focused really heavily on this notion of accuracy. And that's mostly because, in the research community, we want to get published. And the way to get published at CVPR is you get 2% better on some benchmark. And people are like, oh, this is the new state of the art. And you get in and people read your work, et cetera. And I think there's been sort of a hyper-focus on a few particular data sets, especially in vision, and getting really good accuracy numbers on those data sets. And I think people have, to some extent, ignored or sort of downplayed issues of speed and scalability. So a lot of my research actually focuses on these two issues as basically core components in computer vision systems. And in speed, I focus on high-level algorithmic improvements to make our systems faster, and then some low-level optimization approximation techniques. And with scalability, I've been focused a lot on taking information from disparate sources of data, combining them together to build object detectors that can leverage information from a lot of different sources and capture a lot of this richness that we know exists in the visual world. So before we get into all of this, just so I don't lose people, I want to give people a little bit of kind of a history of computer vision, how we got to where we are, what kind of background knowledge you need to know to really get into this talk. So I really like this comic. It came out right around the time that I was starting grad school. A person goes up to a programmer and says, hey, when a user takes a photo, we're making this app. It should check whether they're in a national park. OK, I'll just look it up on GIS, right? And they should check whether the photo is of a bird. I'll need a research team in 5 years. This wasn't quite true in 2014. It was very true in something like 2010. This comic came out in 2014. It was still sort of accurate in terms of the state of computer vision then. But I think this is interesting because it's been about 5 years since then. So I think it's time to give a little update in terms of what kinds of things we've been working on. So I'm going to now switch over to my laptop, which is running sort of a modern computer vision system. This is an image classifier. And we'll wait. So this laptop is running our classifier. I'm pointing the camera at the screen, which is showing the bird that you just showed, or you just saw. It's recognizing, OK, that this is a snow goose. We can try this on other birds. These are cormorants. These are cranes. I had to look this one up. Mew is apparently a kind of gull that lives on the Pacific coast or something. I'm not a bird person, but this is a golden eagle and a parrot. You can see there's some weird stuff happening just in this data set. There are clearly a couple different labels that all mean the same thing. There's parrot and macaw. We won't worry too much about that. But you can see that not only can modern classifiers tell whether or not there's a bird in an image, they can tell specifically what kind of species of bird. And this classifier is actually trained on 22,000 different object categories, so it can recognize all sorts of things. This is an auditorium. I'm not sure how it'll do. Yeah, so that's a giraffe. That's actually like a toy giraffe, so it didn't quite get that right. But I got zebra. It'll probably get laptop, computer screen. It's still confused if that's a computer screen or a parrot still. So let me just switch back. So modern computer vision systems are actually pretty good at this task. But in practice, it's actually really hard. If you think about this from the computer's perspective, here's what the computer sees, right? So who can tell me what class this image is?
It's a zebra.
Zebra? Okay. I should have pointed at it. Actually, I can do this. I'll just tell you what it says. It says ultramarine. It's sort of getting the color, I guess, more than anything else. I don't know why it says that. Well, if you're a person and you're looking at the pixel values, you can pretty quickly tell that this is a dog. I've added in color in this, but in grayscale, you can still tell it's a dog. So how do we go from this representation to understanding what's actually going on in this image? This is what computer vision is all about. And the way that we've started thinking about this kind of problem is image are basically these functions where we're mapping in some space, we're mapping x and y coordinates to pixel values. And we're trying to look for interesting things that are going on in these images. And one thing that you might think of looking for are things like edges. And edges are just rapid changes in output. And we know how to find rapid changes in the output of a function. We just take the derivative of that function. So what we're going to do is borrow some techniques from signal processing. And in particular, we're going to borrow this notion of convolutions, where a convolution is just taking a filter of some specified size. In this case, we're using a 3x3 filter. And the filter has some weight values. In this case, it's the constants a through I. And we're going to apply those to various locations on our image and create some output image. So the output image is just going to be a weighted sum of applying this filter to some local patch on the input image. So basically, we're going from an input image, running this filter over it, and producing an output image. This seems like a pretty simple technique, but we can actually do some really powerful things with it. These are called Sobel filters. They're the filter that you see on the top and bottom. And basically, these are taking discrete derivatives, right? So if you remember what a derivative is, you can pretty clearly map that definition onto what these filters do when you actually apply them onto a function. So the top filter is taking the derivative with respect to changes in x. The bottom is taking the derivative with respect to changes in y. So already just using these convolutions, we can start doing some powerful feature extraction. We can take derivatives of this image function. Then once we have the derivatives, we can do some fun things, like if we take the magnitude of the derivative, we start to get edges in our image, right? But we can also do things like take the arctangent, and we have orientations for those edges. So now, we have an image, but we've gone away from pixel values, and we've moved towards these oriented edges. Now you can start thinking about things like, well, if you have a bunch of edges that are all pointing in sort of the same direction and are the same length away, we can start coming up with some notion of circles. Maybe you put together a few circles and a few lines. You have something like a bicycle, or a few circles and a few lines. Maybe you have something like a car. So now we start pretty quickly getting from this notion of these low-level features, things like edges or circles in images, to notions of objects, where objects maybe are just collections of these lower-level features in images. This starts to run into some problems, though, once we get into the real world. The real world has high visual variability, and static filters like this don't work very well. So you can imagine we could try making static filters for this dog, but the dog can change orientation and position very quickly. And you can't really make a filter that captures all of this variability to any extent with high reliability. So instead of specifying basically exactly what we want to look for, maybe with a bicycle you can specify exactly what a bicycle looks for, or what a bicycle looks like. But with something like a dog that has this high visual variability, we're not going to specify exactly what dogs look like. Instead, we're basically going to try to learn it from data. And the idea here is basically we're going to have some images, we're going to do some feature extraction, we're going to run them through some machine learning algorithm, and we're still thinking about this task of just being sort of a classification task, right? So the task is just predict if there's one object in an image, what is that object? And in this case, hopefully it predicts dog. So old school classifiers had a pipeline that looks something like this. Basically, you'd have an input image, you'd do some kind of normalization, you would do your gradient computations. These are just the Sobel filters that we already talked about. And then you might have some pooling steps, some aggregation steps. You would take these filters and try to combine them together, look at local regions, do some smart things, and eventually you feed it into some kind of machine learning system. So basically the beginning of this is all this hand-designed feature extraction that took a lot of work and effort for machine learning researchers to figure, or for computer vision researchers to figure out exactly what steps were important. And then just this last little piece, we would throw it into a machine learning system like an SVM and make a system that would, say, classify person versus non-person. And one question that you should have right away is like, well, we're learning this last little system, and that's helped a lot. Why don't we learn this whole pipeline? And that's basically where deep learning comes from, this effort to learn this entire pipeline from end to end. And the idea here is we're going to replace all of these individual steps in this pipeline with just convolution operations and pooling operations, convolution operations and pooling operations. And so you saw earlier how convolutions have this really powerful ability to extract features from images. And the interesting thing about convolutions is that the output of a convolution is itself an image. So you can think about taking the convolution of some bank of filters on an image and doing something like extracting edges, and then running more convolutions on top of those images, et cetera, and extracting basically higher and higher level concepts from your image in this manner. So with deep learning, we're still using this primitive operation, these convolutions, to extract features, but we're not using static filters anymore. We're going to learn the filters from data, and basically, we're going to build on top this higher and higher level representation of our image. So at the lowest level, these are actually what the filters look like in a trained network. A lot of them tend to be sort of oriented edge detectors. So if there's an edge in this orientation versus an edge in this orientation. Some of them are texture filters. You can see the ones that look sort of like this are mostly looking for texture in images, maybe like patches of fur or something like that. And there are some different patches for looking at things like color, especially like blobs of color in certain locations. So early on in our network, we're going to look for these low-level features, things like edges and color. Later on, we're going to start building up higher representations, things like curves and shapes. And then we're going to basically put together different curves and shapes and start making more complex object scenes. And finally, we have some sort of linear layer at the end, which is going to basically output some probability distribution over the possible classes. And that's how your basic image classification system works. Sometimes I have some problems with this demo. It's never my software. It's always this camera. This camera has some issues with it. But we'll get that working again. So we actually have gotten pretty good at doing this task of image classification where you just have a single object in an image and you want to know what it is. And the question is, if we show an image like this to our object classifier, what is it going to do with it? It tries to make some predictions, right? It's predicting something like bicycle, but just giving basically a single label to an image like this is missing, obviously, a lot of what's going on in the image. There isn't just a bicycle. The bicycle maybe is like the main object in this scene, but there's a lot more going on. So if we want to perform object detection, and we have this really powerful tool of image classification, one thing you might think of just off the bat is like, OK, if we want to perform object detection, let's run a classifier at a bunch of different points in an image. And this is how people basically started doing the task of object detection using deep learning. So you would zoom in on one point in the image, and hopefully at some point it says, OK, this is a dog. And then maybe you'd look somewhere else in the image, and it would say, OK, this is a bicycle. And then maybe you'd look somewhere else in the image, and it would say, OK, this is a van or a passenger truck. It said hearse in there for a second. And this technique works to some extent. And this is the basis for RCNN, which is one of the early efforts in doing object detection using convolutional neural networks. And the idea is basically, OK, we have some image. We're going to input it into our system. We're going to calculate region proposals. These are basically oversampling the space of possible areas where there might be an object. So let's look at a bunch of different possible bounding boxes that might contain objects. And then we'll just classify each of those areas independently. So for each of these proposals, we're going to run them through a convolutional network. We're going to extract some features. And then we're going to take these features and classify them with an SVM to say whether or not they're actually an object or whether they're just background, for example. And then we need to predict those bounding boxes that I showed you originally. So we're going to predict some kind of bounding box regression using something like a linear model. But there's a pretty glaring problem with doing an approach like this, which is that we have to run this convolutional network thousands of times for a single image to get any results. And this ends up being a really slow process. So this was sort of the state of the art when I started working on my graduate research. And so the first thing I thought was, OK, this doesn't seem to make a lot of sense. We have neural networks. We know they're really good at learning things. Why are we taking these classifiers and trying to repurpose them to perform detection? What we really want is basically, let's take an image, let's run it through a convolutional network just one time. And when we run it through, that should produce all of our detections for us. And maybe we'll have to do some thresholding to get rid of sort of the lower confidence detections. But what we really want is a system like this, where we just have to run it through once. So the key idea is we're going to reframe object detection as this regression problem. And we can model it with a single neural network. So now instead of basically looking at a single image 2,000 times with a convolutional network, you only look once. And that's where the name YOLO comes from. So this was our object detection system. And the problem here now is how do we represent this problem of object detection in such a way that we can model it with a single neural network? neural networks do really well when there's a fixed size output for a problem. That's why they work well for classification. You're basically predicting a fixed length vector. But for something like object detection, there might be one object in a scene, there might be 20 objects in a scene. You need to be able to basically handle that variability in terms of the output space in some sort of principled manner. So what we did was basically designed a tensor where we could encode detection. And what I mean by that is we have this fixed size three-dimensional tensor that encodes both spatial information and also class information for objects that might be in the scene. So the way you can think about this is imagine that we have an input image into our system. Imagine just splitting that input image into some sort of grid. And at every location in this grid, that's sort of the spatial component of this three-dimensional tensor, we're going to predict a bunch of channels, and each of those channels will correspond to different things. So at every location, we're going to predict a bounding box, and we're not necessarily saying that there is an object at this location or not. We're just going to predict something. And we're also going to predict the probability that that bounding box contains an object. And here we want, the bounding boxes, for example, predicted by, and in particular, the grid location that is located at the center of an object is responsible, we think of, for predicting the bounding box for that object. So for example, if you look, it's hard to kind of disambiguate which bounding boxes are which, but the bounding box that's being predicted by the grid cell at the center of the dog is predicting the bounding box for the dog. So we're predicting the probability that every bounding box contains an object, and in particular, we want these predictions to be high for the bounding boxes that actually contain objects and low for all of the other ones. And we're also predicting class probabilities. And in particular, these are conditional class probabilities conditioned on the probability of whether or not there's an object. So one problem that you run into in detection is it's kind of this imbalanced problem where most of the time in most of the image, there is not an object of a particular class. And so if you think about just encoding this naively as the probability that there's a cat or a probability that there's a dog, most of those probabilities will be 0 in most of the images. And you get this really sort of tricky problem to optimize. So we get rid of a lot of that by basically predicting conditional probabilities where if there is an object there, we want it to predict dog. If there's not an object there, we don't actually care what class probability we end up predicting because we're going to end up ignoring it in the end anyway. But now we can combine together basically the probability that there's an object with these conditional class probabilities. We can just use the chain rule, multiply them together, and we get the unnormalized probability for particular classes. We already have our bounding box information. And now the last step, all we have to do is threshold all of these bounding boxes to get our final predictions for our model. And in particular, this framework is a lot easier to train because we just have this fixed tensor that encodes detections for an image. So all we're actually going to do during training is just input an image into our system, and we'll look at the bounding boxes that we have in our labeled data set, calculate what the ground truth tensor would be. If we predicted the ground truth perfectly, what would the tensor look like? And then we're just going to forward propagate our image to predict our version of the tensor. We're going to calculate some loss for the predicted tensor versus the ground truth tensor, and then back propagate that error through the network and train as you would train a neural network normally. And in the end, this ends up working pretty well. So there are a lot of benefits to doing an end-to-end object detection system. Yeah?
If you go back, how do you get the ground truth detection if it seems to be, depending on the size of your boxes, it will become a very expensive proposition to label ground truths?
Yeah, labeling. So fortunately, we have a lot of labeled data sets that we use. In particular, there are a couple that you talk about a lot in detection. The Pascal VOC data set has 20 object classes and on the order of about 20,000 images. And the COCO data set has about 80 object classes and about 100,000 training images. And these are basically labeled by like Amazon Mechanical Turk I think Cocoa was labeled by Microsoft's internal labeling system. But yeah, these all have to be hand annotated. And this is a really expensive process, right? With image classification, it's pretty easy. You can search, Google for like pictures of dog and then do some minor filtering after the fact. But if you want to label for object detection, it definitely takes a while. So we leverage data sets that already exist.
And do you need each object to be in every position in the image?
Good question. We would like that because ideally we want systems that are robust to changes in viewpoint, there's lots of changes in lighting especially too. There's lots of variability that happens in the real world. How we deal with that in practice is that we do a lot of data augmentation. So you take images and you resize them in a lot of different ways. You flip them back and forth. We also do lots of things like color manipulation. So, one problem with deep learning, you're always kind of data limited. So you're always looking for ways to avoid overfitting. And a good way to avoid overfitting is to do extensive data augmentation. And that also means that you end up seeing objects in different locations in the image and in different orientations and things like that. Yeah, so doing data augmentation is very important to this task.
How do you decide your group size?
You try out a few and see what works well. Yeah, it's a hyperparameter you tune. It's not necessarily important in that we have some experiments showing that you can use a variety of different grid sizes and it doesn't end up affecting sort of your final results as much as you might think. But it is something that you sort of have to tune depending on the data set that you're looking at. Good questions. So there are lots of benefits to doing this kind of end-to-end object detection. One thing is speed. So we went from basically evaluating a neural network 2,000 times per image to just a single neural network evaluation for an image. So performing detection in this manner is much faster. We also get some cool properties that you don't get from a system like RCNN or a system that's considering detections sort of independently. So we have this contextual modeling that happens because we're running on full images. Images are evaluated as a whole, which means that the network learns things like if there's something that looks sort of like, maybe it's a horse or maybe it's a dog, but maybe there's a person standing next to it. You can start learning some of this contextual information like, well, people are generally a little bit smaller than horses, but a little bit bigger than dogs. And so we can start basically modeling some of that implicitly in our network and start improving the performance along some of those parameters. It's also a lot easier to train with systems where you're doing something like visual search. You have a high number of negative images. Remember that you're extracting something like 2,000 region proposals for RCNN. Most of those are going to end up being negatives. And most of those are going to be easy negatives. So if you just train your network sort of naively, you end up not doing very well because you learn really well that the easy negatives are negatives. The hard negatives don't end up contributing very much to your loss. And so you have to do a bunch of hard negative mining and a bunch of optimization tricks. With a system like YOLO, you're training on these full detection images already. You don't have to end up doing that hard negative mining. The optimization ends up just kind of working out well by itself. We also have experiments that models like this generalize a lot better. So in particular, we transferred some of these models to doing person detection in artwork that were just trained on person detection in natural images. And this remains to be studied a little bit more, but for reasons that we don't entirely understand, it seems like doing this sort of end-to-end training on full images, probably because we're not overfitting as much to these particular bounding boxes, but actually looking more holistically at the image, we end up not overfitting as much, and we end up being better at sort of some of these transfer tasks. And in particular, speed is obviously what this started with, and exciting for me, yeah.
Yeah, I was wondering, are you able to extract which convolutions are capturing that context and maybe see if that's what's causing the generation?
I wish. Yeah, it's still a very open problem in computer vision interpretability or doing sort of understanding what the network is learning. So there is a lot of sort of open problems in this domain of like which pieces of the network are performing which parts of the computation, which pieces are contributing, et cetera. And so speed is obviously where this all started. So with RCNN, it takes like 20 seconds to process an image. If you think about a car moving at highway speeds, it would end up going about a third of a mile in that time. So if you wanted to like use one of these detection systems in practice, obviously a third of a mile is a really long time, a really long way to travel for your autonomous vehicle, essentially moving around blind, right? So with YOLO, it takes 20 milliseconds to process an image. That's about the time it takes a car to move 1.7 feet traveling at highway speeds. Obviously, this kind of system would be a lot more safe for anyone in the car or sort of external to the car. So just to help motivate a little bit why speed is still so important. So Pascal, as I talked about, Pascal VOC is one of these standard benchmarks. I'm not going to go into what mean average precision is, except that it's like sort of like accuracy, and that 100 is perfect, 0 is bad. So DPM, the top entry here, is pre-deep learning. How good were we just with these sort of hand-tuned feature extraction and these linear SVMs? Gets around 33 mean average precision. When we go to these deep models, we start getting into the 60s and 70s. YOLO operates at a little bit less accuracy, but much higher in terms of speed. So going from either 20 seconds or 2 seconds to 22 milliseconds. And so, this was a few years ago. We thought this was a pretty cool idea. Submitted this paper to a major machine learning conference. And people for a long time in the vision community had sort of thought of detection as like visual search. Detection is like sliding window or applying classifiers to various places in the image, right? So signed reviewer number 6 said, personally, I'm not a fan of end-to-end. Reviewer number 3 elaborated a little bit more. Personally, I find the overall concept of reducing detection to predicting a bounding box for each cell to be somewhat unappealing, and we got rejected. And I think this was actually kind of an indication that we were onto something, right? Having reviewers say that they like, not that necessarily your paper was bad, but that they just didn't feel good about it. It was like, oh, we're really rattling the cage of computer vision researchers. So we just resubmitted to CVPR, and we actually won the OpenCV People's Choice Award at CVPR 2016. And we worked a little bit harder on improving things, came out with YOLO v2, which had significantly higher mean average precision, still operating at these kind of real-time speeds, and got Best Paper Honorable Mention at CVPR 2017. And finally, recently, we've come out with YOLO v3, which, again, we're always trying to make these things more accurate. And we can do a little demo, basically, of what these different systems look like. Can see what all of you are up to now. It's going to take a second just because it's loading all 3 of these models in so I can demo them all. So YOLO v1, oh, the camera dies sometimes, as I said. So YOLO v1 isn't the most accurate in terms of its predictions. The other thing that I can do is just use this webcam, which I have as a backup. It's not as much fun because you can't do cool things like zoom around with it. YOLO v1 obviously isn't the most accurate in terms of its predictions, but really just pushed the state of the art very far in terms of speed. So this is sort of the first version. You can see it sees like a lot of you. It probably can't necessarily see that bottle. Probably gets some of these objects more or less correct occasionally. There's a big jump in terms of what YOLO v2 can do. So now it's getting a lot more of the people kind of in the background. We're getting a lot more of these objects. It's still, the polar bear is hard. Also, a lot of these, they're toys, right? So it's not actually a zebra that it's seeing. There's some contextual information that is kind of tough for the model. There's not a huge jump in terms of YOLO v2 versus YOLO v3. How does it do for that bottle? Yeah, it gets the bottle. Yeah, gets laptops. Very weird things happen when you point at it itself. So we try not to do that too much. Switch back over. So another just interesting aspect of YOLO v3, and this is no longer a current sort of figure, but was accurate about a year ago in terms of the state of the art. This is on Cocoa, which is a lot less saturated of a data set than Pascal VOC. We're still hovering, in the sort of 50s range in terms of mean average precision. So there's a lot of work still to do. But I'm really sort of proud of the fact that YOLO v3 is pretty far out in terms of the frames per second that it gets, especially when you think about this trade-off between accuracy and speed. We managed to have this really performant detector that still has fairly high accuracy. Another cool thing just about YOLO v3 in particular was a multi-scale training methodology that we came up with that allows us to basically use the same model and the same weights. And all you have to do is change the input image size, and you can decide basically on the fly this trade-off between how fast the model runs and how accurate it is. So that's what you're seeing here. The 3 different YOLO benchmarks are at 608 by 608 resolution, 416 by 416 resolution, and 320 by 320 resolution. So this just provides practitioners this really easy kind of knob that they can twist. And this is, again, all the exact same weights and the same configuration file. All you have to do is just change, in terms of the network, how big the image is that you're feeding in. So that just makes these things a little bit easier to use, which is nice. In terms of impact, nowadays we get about 25,000 visitors to the project website per week and about 5,000 downloads on GitHub. So a lot of people are using this for a lot of really cool stuff, which is really exciting. It's spawned research in autonomous driving, in medical domains, in robotics. Ecology, I think, is one really interesting domain. People are using object detection for surveying large populations of animals in things like natural parks. We have papers have spawned off of this in information retrieval. I thought this one was interesting. Cryo electromicroscopy, which I'm not sure what that is. Astronomy and aerospace, and many, many more papers who have sort of taken this kind of core building block in computer vision and been able to use it for their own problems and their own domains. And this is something that's really exciting, basically, about building these low-level tools, is you enable people to do research in their own field and solve their own problems in a way that I can't go out and solve all of the work in all of these different fields, but if you build these core components, then people can use them for their own tasks, and that's something that's really exciting, just in terms of maximizing the impact of my research. This is one of the things I'm most proud of. Is every so often, we're usually around 2 or 3, but every so often, if you Google YOLO, we'll be the top result on Google too, which is always nice to know that your research has supplanted a major meme, at least in terms of search engine optimization.
In the other applications, are people training it with their own sets of data, or? Yep,
exactly. So, and this is a very general framework. So I showed you a model that was trained on. I showed you a model that was trained on the Cocoa data set, but we also have models trained on many other data sets. This one is trained on the Open Images data set. The place where you'll see the difference is it can do things like eyes and nose and glasses, especially if I turn down the threshold for how confident it has to be. Gets ears in there sometime. So it's a very general purpose object detection system. We've trained it on a few particular data sets, but people come with their own data and train it on their own data sets and use it for all sorts of application domains.
How much training data do you need?
Well, it depends on how good you want it to be.
Wild, right?
Yeah.
How many gorilla images during
I think a decent benchmark is on the order of 1,000 labeled images per category. That isn't perfect, but that's a rough estimate in terms of magnitude. So many.
How do you deal with hyperparameter optimization? So what are the layers? The pooling layer, the convolution layers, what is the size of the convolution layer,
Yeah.
et cetera? How do you deal with that?
Great question. I should be doing this, but the question is, how do you deal with things like hyperparameter optimization? And the answer is, we try a few things, and we hope that our models aren't super dependent on hyperparameter optimization. And for the most part, we leave that to like Google and Facebook because they have a lot of resources. So in particular, like a lot of these decisions come down to like what's the base network architecture that you're using. And big companies have the resources to try out a lot of different things, and they do. And then some of that gets filtered back into the research community, and what are kind of best practices for designing these networks, et cetera. And that's a whole other avenue that we can go down, is like, how do you design neural networks to be efficient, to sort of maximize, the computation that they have. And that's something that is very important for getting systems running in real time, in any capacity.
So I'm wondering, the first image classifier example you brought up, where it was just doing like sort of whole image classification, you had it like classifying with a greater diversity of, say, like birds.
Yeah.
Is that something that can still be held true into this? That you
We'll
can
get to that.
Specificity?
Yeah, that's the second part of this talk. Don't worry. We'll get there. Well, I guess the third part of this talk. Which I have to watch out for. I came here and showed you some cool demos, and I did that because I have a $4,000 laptop that has its own desktop GPU in it. And in particular, if you go into any deep learning researcher's lab, they have, probably multiple machines that look like this. I think my count is up to like 13 machines that I've built that look like this. So on the order of, like 60 GPUs that I've bought from NVIDIA at this point or something. Deep learning researchers have these massive computers with lots of compute. Real people have, some cell phones, right? And convolutional neural networks are really expensive. So the networks that I'm running have, like 3.8 billion operations per layer, about 37 layers per network, 141 billion operations total. Our Titan X GPUs have about 10 teraflops of compute, and an iPhone X CPU has 124 gigaflops. So our detection needs to be 100 times better to get from something like this to something like this. So the next question, obviously, is like, how are we going to do that? How are we going to bridge this gap? And in particular, this is work that I did with some researchers at the Allen Institute for Artificial Intelligence. We did a little survey, and when you look at kind of the surrounding literature, neural networks are super redundant. It seems like basically these 32-bit floating point operations aren't actually necessary to getting networks that work well in practice. 8-bit fixed point seems to work pretty well. Ternary weight seems to work pretty well. So it seems like we can start quantizing these weights down and maybe getting more efficient networks. And our key idea for sort of this research direction was we can actually just approximate convolutions using binary input and binary weights. So just ones and zeros for all of the weights and the inputs. And then we can implement these really expensive operations just with binary XNOR and PopCan operations and make these networks be very fast. So how we're going to binarize these convolutions, you can imagine, well, we have some weights and we have some input. Why don't we just take the sign of the weights, right? And that's a really easy way to get these things to be between 0 and 1, or to be just 0 or 1. And you end up basically with pretty large quantization error. And we know this because prior work tried doing this and ended up not getting very good accuracy. And so what we're going to do basically is just add on another constant, which ends up just scaling the weights by some amount. And what that amount is going to be is actually just the mean of what the real value floating point weights would be. This intuitively makes some sense. If you think about doing like PCA on unnormalized data, your first principal component is always the mean. So that contains a lot of information in terms of what's going on. And in particular, if all we're doing is after the fact multiplying by some scalar amount, that doesn't actually add a lot in terms of how much computational resources we're using. That's just a multiplication by a bunch of numbers is actually pretty fast. The thing that's taking up a lot of time is this convolution operation. So if we just binarize the weights and we use this sort of extra scalar value, we can go from doing real by real convolutions to real by binary convolutions. Instead of basically using multiplication operations, we're just going to use addition and subtraction because all of our weights are either going to be +1 or -1. And we get basically a very large savings in terms of the memory footprint of our models because all of our weights are no longer floating point. They're just these binary weights. And we actually don't really lose anything in terms of accuracy. If we train AlexNet on ImageNet, we actually gain a little bit in terms of accuracy. This is probably more just due to the fact that AlexNet is super over-parameterized. So we're introducing basically some more model regularization. But we can go further than this. We might want to binarize the input as well. And we have the same problem if we just take the sign. So what we want to do is also have this additional constant that we're going to multiply by. But now we have this problem where the constant is actually inside of this convolution. So we have to kind of pull it out. And this constant is just going to be the spatial mean. So the mean across channels for every spatial location. And the way that we can pull that out of this convolution operation is just by convolving it with a box filter, which ends up being a pretty fast operation. And we end up with this k constant value matrix and our alpha that we already had before, which is the mean of our weights. And now both sides of this convolution operation are binary. So on one side we have the sign of the input, on one side we have the sign of the weights. And we actually know how to do that really well. It's just a lot of binary dot products. And it turns out that you can do binary dot products really efficiently just with XNOR operations and with pop count operations. So by adding on a little bit of this upfront cost in terms of computing alpha and k, which tend to be fairly easy to compute, and then after the fact you have to multiply them by your final result, we can replace this full 32-bit floating point convolution with this convolution basically just in terms of binary numbers. And so for training this, we end up doing basically a form of projected gradient descent. So we're going to forward propagate and backward propagate using the sign of I and W. And then when we update W, we're going to update actually a real valued version of W. So during our propagation steps, we're using this binary representation. But always in the back of our head, we have this real valued version of W that we're actually doing the updates on. And we have to cheat a little bit because we have this sign operation, but we want everything to be differentiable in our neural networks. So we're going to just make up a gradient for the sign of x. And in this case, the gradient's going to be 1 if x is between -1 and +1, and it's going to be 0 otherwise. And so when we do this binarization, we save a lot in terms of memory and now in compute as well. So in our operations, instead of doing these floating point operations, we're just doing XNOR and pop count operations for most of our convolution. We still have the same memory savings, but in theory, for computational savings, we can bin all of these together into 64-bit longs and do these bitwise operations and save a lot. It turns out in practice, CPUs are pretty heavily optimized for floating point computation, so you don't actually end up saving as much. And we do lose a little bit in terms of our accuracy, but in practice, it ends up working pretty well. Let me see if this demo is going to work. And the great thing about this model is that it's kind of independent of it's kind of independent of the task that you want to do. It just applies to any neural networks, right? So this is running image classification. So it recognizes that this is a laptop. Maybe it'll recognize sports car, but also piggy bank is in there. So you can tell we're losing a little bit in terms of our... we're losing a little bit in terms of our... Oops. We're losing a little bit in terms of our accuracy, but we can also, instead of just running image classification, we can also run things like object detection on our cell phone. And this is actually like a really big advance. This is something that people in industry have been telling us, they really want to do. They want to be able to run image class or object detection, but instead of just on these big GPU machines, they want to run it. Let's see if it gets these zebras a little bit. It gets one of them. Gets that horse, kind of. And again, these are like, this is kind of hard, right? Because this isn't actually a car. This is a toy car. So give the model a little bit of credit. Gets that that's a giraffe. So being able to do basically these XNOR nets, we have a lot of benefits. In particular, we're evaluating on device. This is evaluated on the CPU of this iPhone. So we're not using any GPU primitives. We're not using any of sort of like the machine learning stuff that Apple provides. We're actually just running on the CPU itself using these binary operations. So we get to be a lot faster than like something that requires a big GPU. We also get gains in terms of latency. So the other way of doing this is having some cloud server somewhere that evaluates your image. But now there's not this round trip time to the cloud, right? All of the operations are just happening on your device. And we also get some benefits in terms of security and privacy. So the data is staying on your device. If you think about an application like a camera, like a security camera that's checking who's entering your door, who's around your house, you don't necessarily want to send video of everything that's happening in your house to some cloud company somewhere. It turns out that a lot of these security cameras are manufactured in China, and the companies have pretty close ties with the Chinese government. So a lot of that information ends up getting forwarded over to governmental figures. So there are definitely some security and privacy implications for being able to do these operations on device, which is very cool. So switching gears a little bit, and I'll just blaze through this pretty quickly. The other thing I'm really interested in, aside from speed, is basically being able to scale these models to, as you were saying, with the classifier, we can recognize 22,000 classes, but with object detection, we were just doing like person and horse and stuff. And that's because, as we were alluding to earlier, labeling for detection is really hard. So with classification, we have these massive data sets. ImageNet has 14 million images, 22,000 classes, but it just has these class labels, basically. So like this whole image is just labeled with golden eagle. Whereas with a detection data set like COCO, we have far fewer images, but we have these really rich labels that say, this object is located exactly at this position. These are the bounding box coordinates, et cetera. So, one thing we might want to do is there some method by which we can basically combine these disparate sources of data together and be able to train on both of them at once so that we have a detector that has the same power in terms of objects that it can recognize as this classifier that we've already sort of demonstrated. And the problem with this is, typically classes we think of as in this flat hierarchy. So for COCO, we have these 80 classes. For ImageNet, we have these 22,000 classes. But basically, these labels are sort of mutually independent. So we end up just running a softmax operation over our unnormalized probabilities. We get a nice probability distribution. We know that an image is just one of these possible classes. But we can't basically just smash these labels together into one big data set because we start having collisions. So if we have a bear, for example, it might be the bear from the COCO data set, or it might be the American black bear from the ImageNet data set. So we need some more basically structure to put on top of our data to be able to do this combination in some sort of sensible way. And WordNet, which is sort of the underlying label source for ImageNet, already has some structure, but it's pretty messy. So it's this graph-based structure. And what we decided we really wanted for this was a tree structure that we could do this data set combination on. So what we're going to build is basically a tree, and we're going to use this structure in WordNet to create a hierarchy and then combine our data sets together using that hierarchy. And the way that we're going to build this tree is just create sort of the smallest tree that we can that has the fewest extraneous nodes that we don't have images for. So we have a lot of images associated with particular nodes in this big graph. And so we're going to build a tree that has the fewest sort of extra nodes that we don't have images for. So you can think if we just sort of have dog in this example, if we just have images for dog and none of these other kind of internal nodes, then sort of the shortest path through this graph would go down from physical object to dog and bypass, mammal and carnivore and canine. So in that case, we would just kind of forget about those internal nodes completely. In practice, we actually have other canines. We have things like wolf. So what we actually want is a tree that looks something more like this, and maybe we'll just forget about domestic animal entirely. And this is the process by which we build up this hierarchy from this graph structure that we have. And so what we end up with is word tree, which is a tree-based structure of all of the categories in both ImageNet and COCO that have images associated with particular labels. And in particular, now we can basically map both sets of labels onto this one tree structure, onto this one hierarchy. So in blue, we see the labels that are associated with the COCO dataset. And in red, we see the labels that are associated with the ImageNet dataset. And now we don't have this same kind of collision. So if we see a dog in the COCO dataset, we know which label that is. And we don't necessarily know what particular breed of dog it is, but we at least have partial information in terms of where that class should belong on this tree. So now all that's left is, we have a method at least of combining these label spaces together. How are we going to train on this data for doing something like detection? What we're going to do is imagine, again, I really like conditional probabilities. We're going to imagine that each of these nodes is a conditional probability conditioned on the class one level above it. So, the node for dog isn't actually the probability that an image is of a dog or that a bounding box is for a dog. It's the probability of dog given canine, and canine is the probability of canine given mammal, et cetera. So if we want to predict, the probability that some bounding box is of a Bedlington Terrier, then we take the probability that there's an object there, which is predicted by our model already, right? That's our objectness prediction. And then we multiply down through this tree all the way until we get to this leaf node, which is probability of Bedlington Terrier given Terrier, et cetera. And we have to figure out how to map this in terms of the neural network primitives that we have. If we were just talking about like a flat hierarchy like ImageNet, we would just do a softmax operation over the entire label space. For predicting these hierarchies, we are just going to do multiple softmaxes over sibling nodes. So we know that, or we're going to impose basically on this system that the sibling nodes are mutually exclusive. So you can't be basically, let's see, one of these trees. You can't be a ground vehicle and a water vehicle and an air vehicle. You kind of have to pick. That doesn't end up always panning out in practice, but in terms of the label space that we're going to impose, that's how we're going to do it. And then we can just predict unnormalized probabilities for all of the nodes in this tree, use softmax operations on sibling nodes to get basically well-formed probability distributions. And that's how we can predict basically this whole tree structure by just predicting a single vector of probabilities. And using this structure, we train YOLO 9000, which is our sort of advanced detector that has a lot of these object classes from ImageNet in it. So what we're going to do is when we see detection data, we basically backpropagate our full loss because we have objectness information, we have our bounding box information, and we have the correct class that we want to predict. And sometimes we just see classification data. So we're basically going to feed in both sources of data. If we just see classification data, we're going to pick the prediction that is already the highest for the correct class. And then we're going to try to make it more confident in that particular prediction. And so that basically what we're doing is just taking the information that we have and only backpropagating loss based on the information that we're sure about. We know that there is an eagle in this image. We're not necessarily sure where it is, so we can't backpropagate, for example, information about the bounding box. But we can backpropagate classification information to make it more confident, in this eagle prediction. And so in practice, this ends up working really well. So again, we have classification information for things like German Shepherd and Husky, but our detector has never seen an image that has labels associated with it that has both of these dogs in it at the same time. And yet, at test time, we can actually end up predicting basically correct bounding boxes. So the bounding boxes are correct because it's seen a lot of dogs and is used to predicting these kind of bounding boxes. And the class predictions are correct because we've learned from our classification data in sort of this weakly supervised manner to predict the right classes for these particular dogs. Our detector has seen cats before, but it's never seen a cheetah. It's seen like horses, which aren't quite antelopes, but are similar enough that it can kind of get the bounding box right. We make some mistakes. It thinks the chips are edible fruit. I don't really know what's going on there. The unicycle thing I think is interesting because clearly, it has bicycle in the data set, but it doesn't have unicycle. But still, it manages to kind of lock in on that wheel. And there aren't any bottlenose dolphins, just period, in our detection data set. And yet somehow we still manage to predict a pretty clean, good bounding box for this object class that is only ever seen in our classification data. Same with this whale. There's no whale in our detection data set. This gives you just sort of a little bit of a feel for where these bounding boxes come from. It's seen carrots in the detection data, for example. So it can, it sees this and it thinks, OK, that sort of looks like a carrot. And I know how to predict bounding boxes for a carrot. And then during the training process, presumably over time, it starts out by predicting some good bounding boxes and then slowly updates its classification information to hopefully at some point predict chanterelle. So now we can predict a lot more classes with our object detector than we could before. There's more, but we'll forget all about it because we're out of time at this point. So I guess in the future, I'm interested basically in working on some of these extensions, like embodied vision, so vision for robotics. Also, this is a fun project that we did trying to model the vision that my dog has. So these tasks in things like unsupervised learning. And this is also a fun project where basically we're looking through images like this to try to count seals and polar bears. So basically continuing to improve our detectors and make them more usable for people in the real world. All of the models and the fun things that you've seen are in Darknet, which you can go download and start playing with yourself. It's on GitHub. It can play Go. It can identify birds in Twitter competitions. Thank you to my co-authors. And I can take any additional questions that you might have.
We are almost out of time, maybe 1 or 2 questions, but we do have a reception here. So
I'll be around and happy to talk
you
offline.
will be around, captive audience. So maybe 1 or 2 questions.
So how's the speed when you train with the 9,000 classes?
Yeah, it's actually, it runs just as fast as, so the only component of the network that matters for classification is just right at the end. So actually it runs in about the same amount of time. There's a little bit of problems just in terms of doing things like non-max suppression when you have a lot of classes and some weird kind of things like that that you wouldn't necessarily think about. But in practice, it works pretty well. It takes sort of a hit in terms of the bounding box accuracy and stuff like that. So it still is getting things like, and it also tends to like occasionally make weird predictions for people. So I don't always like running it. All of you are apparently leaders. Yeah. So this is a Dixie cup, which we don't necessarily have Dixie cup in our it gets these cords sometimes, not just LCD display. So it still works to some extent, but racer, self-propelled vehicle, or a cellular telephone, one of the two. So that is all pretty preliminary work that isn't necessarily up to the same standards in terms of when you just train on classification data, you get very good models. When you start trying to extend it out to, or when you just train on detection data, you get very good models. When you start extending it to classification data, it gets a little bit more noisy.
Right. Is that a quick question, Shalom?
Yeah, coding wise, are you using CUDA, are you using,
Yeah.
for the neural networks, are you using libraries like cuDNN? Or
Yeah. Every neural network framework out there these days is just a front end for cuDNN because they have really good primitives and because they know the internals of the GPU and can sort of optimize really well for, yeah.
So let's thank the speaker once again and take further questions.
Thank you.